Now we'll talk about SRAM, which is static RAM, which is under random access memory. Static RAM or SRAM is a digital device that uses a logic element similar to the processor. It stores binary values, logic 1 or logic 0, in a flip-flop configuration. And it is a non-volatile, so the data inside that particular cell will be retained as long as there is a power connected to the cell. And the capacitor of SRAM is far below the DRAM because it takes more area compared to the DRAM. SRAM is widely used for cache memory, and in this example we have a 130 nanometer technology up until 32 nanometer technology. So with a smaller size, the cell size, if you look over here, the cell size is shrinking with the smaller size. So with this we can reduce the area and we can increase the memory capacity. So this is the basic structure of SRAM. We have address input, data input, the control input, okay, and the data output over here. This is 2n by B RAM. Okay, so this is several example of SRAM devices in 28 packages and 32 pin packages. Basically, for each cell you have in out. This is might be using D flip-flop, so data in to the input, output. So you have a bit line or bit line over here. Bit line over here is to write data. Okay, out. Bit line over here is to read data, and it is connected to the buffer over here and to the output. And in this example we have 8, 1, 2, 3, 4, 5, 6, 7, 8 by 4. So since we have 8 locations, so for the decoder we need a 3 input, so it is a 3 to 8 decoder. And this is the control part, whether we want to write operation or output operation, and this is to select which cell is activated. So it is active low input and active low output. Okay, so in this example I need data from line 3 over here, so I have to put 0, 1, 1, so it will select pin 3 over here. So it is all connected to the select input, so meaning that all the cells are activated, and then we'll read the data. It is connected to the output. Okay, but you have to control the buffer over here by using the control circuitry over here. So it will be output and chip select, so it will be turned on. We enable the output, so we have read the data from line 3. This is an example of one cell. So this is the control line just now. It is a D flip-flop. Okay, so usually the address must be stable before the writing cell, meaning that we have to make sure this is data ready before we can read the output. And we have to be sure what are the operations that we want, whether we want to write or read the data. So the main point is the select line, meaning that we activated that particular cell. In we write, out we read. Okay, so this is the buffer just now. It is bidirectional usually, so that this is going in and this is going out. All is controlled by this particular basic combinational circuit. This is another example using SR flip-flop. So instead of use D flip-flop, we can also use SR flip-flop. The same thing, we have a select line over here that controls the operation of the cell. So this is the bit line. Okay, so this is the output. Okay, and we also can have a SRAM cell just using 12 transistor. In this example we have a inverter back to back. This is the transmission line. So we have a write okay, write B, read, and read B. Okay, it can hold the data. So this is much more simpler compared to if you use D flip-flop or SR flip-flop. This is just one cell over here. Okay, it is called 12 transistor as RAM. Okay, so this is the example of the layout for this particular SRAM with 12 transistor, and the most popular is the 6 transistor SRAM cell. We have 6 transistor, T1, T2, T3, T4, T5, and T6. This is one inverter, this is another inverter. So this is the pass transistor actually. So it is controlled by the address line. We have bit line bar, okay, and we can view it. Okay, this is the first transistor, the first inverter, and this is another inverter. The transistor over here connected to the word line. So this word line will control this transistor, whether we want to put the data in or we are taking data through the bit line bar. Okay, the same thing. Okay, just the first inverter, the second inverter. Okay, so for the read line, we have to pre-charge bit, this one bit and bit B, and then raise the word line. Okay, this is how to read the data from here. So when we pre-charge bit and bit bar, word is on, so we can have data over here. But for the write, we have to put data inside this. The operation is quite different. We look into the details later. Okay, so this for the read operation just now, the pre-charge both bit line, bit and bit bar is high. Okay, then turn on the word. This is on, this is on, so we read the data. Okay, so this is an example of A0, A bar is 1, so bit is discharges. So this is in terms of the output. Okay, and for write operation, it is the bit dengan bit and bit bar will have a different value. This is high and this is low. Then only you turn the word line, and with that you can write the data into the cell. Okay, this is example A0. A is over here, A bar is here because this is inverter. So if it is 1, okay, this will be 0. And this is the timing diagram of that operation. Okay, in terms of sizing, for the 60 cell, we have a different sizes. For the transistor that is connected to the word line, it is a medium size. Okay, and but for the P transistor over here, we can have a weak size, and for the N must be a strong size, meaning that it is bigger compared to this one. Okay, this is an example of the layout. Okay, this is just for 1 bit, so you have inverter, and then you have another transistor over here. So this is the actual layout, and this is for 4 cell, 1, 2, 3, 4. We have 4 cell over here. This is another SRAM design. In this example, they use resistor, but for the resistor, it will take much more area, because resistor, if you want to fabricate the resistor in the you will take more silicon area. So usually we didn't use this, we use a transistor. Okay, this is the 60. And for large SRAM, usually they will break it into several sub-array. So this is array 1, array 0, 2, 3, and then they connect it all together. So with that, we can have a very large memory space. Thank you.